Hey, Dr. O here, and welcome to part 2 of Unit 8. So in this part, I'm just going to preface, we're going into glycolysis and the Krebs cycle. So get ready. Here we go. So in this section, we're going to talk about glycolysis and then getting into the Krebs cycle and basically looking at how cells will take glucose and metabolize it. So let's start off by talking about glycolysis. Now, glycolysis is the breakdown of glucose, and it's an anaerobic process, which means that we don't have to have oxygen hanging around in order for this chemical reaction to move forward. What happens with our glucose? Glucose is a 6-carbon molecule. It's going to be broken down into 2 pyruvic acid molecules, also known as pyruvate molecules, and those are going to be 2 3-carbon molecules. So basically, we just cut our carbon molecule in half, and pyruvate's going to one pyruvate will end up with 3 carbon molecules, and the other one will end up with the other 3. Now there's 3 major phases with glycolysis, and they're outlined right here. So first of all, we have the energy consuming phase, where we have to actually put some ATP into the chemical reaction in order to get it to move forward. Then we have a little song and dance with our electron shuffle, known as phosphorylation and oxidation. And then we have the creation of ATP, which is the energy releasing phase. So let's take a look at each one of these so we can better understand the process that is involved. Now there's going to be a lot of fancy language used on my slides, and I'm going to try to break this down as simply as possible because I know that we're not chemistry majors here, all right? So I'll give you the big picture, and then I'll kind of tell you what the verbiage means. So phase 1 of glycolysis is the energy consuming phase. And basically what that means is that we're going to utilize 2 ATP molecules in order to get this process going. All right, in order to get the glucose broken down from a 6-carbon molecule to 2 3-carbon molecules known as pyruvate, we have to shuffle around some phosphate ions in order to make that happen, and that's what we mean by phosphorylation or something being phosphorylated. We're going to be shuffling these phosphates around. Okay, so this first part is the energy consumption phase. This is where we have to invest a little energy to get the ball rolling. 2 ATP are going to be used, but the good news is that this process will produce 4 ATP, so we end up with a net of 2. Now once we start dividing our glucose up, we can't just take a machete to it and cut it in half and then expect the world to be fine, because the way that molecules are put together is they're bonds between the atoms in the molecule, and when you start separating those atoms, you have to put something back in an area where you broke the bond. So we learned about this in hydrolysis reactions. You just can't like pull a molecule apart and expect the world to be fine. You have to have something there in order to kind of patch that exposed binding site that you just broke apart. So what ends up happening with glycolysis is that we have enzymes, they're called kinases, and they're the ones that are responsible for adding a phosphate to the molecule of glucose when we basically cleave it in 2. All right. So there's different types of kinases, like we have hexokinase and we have glucokinase, and I don't think you need to know the specific sorts of kinases that do that, but what it is good to know is that there are these enzymes hanging out, waiting to slap a phosphate on that exposed binding site after we've had the glucose molecule separated into 2 3-carbon molecules. So this is an image from your book in OpenStax, and this is looking at phase 1. So what we see happening here is that we've got our 6-carbon glucose molecule, and then one of the things that's going to happen is we're going to basically take one of our molecules of ATP and we're going to cleave off a phosphate, leaving behind an ADP, has 2 phosphates, and we're going to take that phosphate and we're going to put it onto one of these corners one of the carbons, I should say, of our glucose. And then with our second ATP, because remember this is a 2 ATP molecule investment phase, we're going to take that other phosphate from our second ATP and then add it to another corner. So basically we've utilized 2 molecules of ATP, leaving behind 2 molecules of ADP. All right, now what are we going to do? Well, we're going to do something with those phosphates that we added to our glucose molecule. So we basically created this molecule known as fructose 1,6-biphosphate. Basically, it's a glucose molecule that has 2 phosphates to it, but we're going to split it into those 3 carbon fragments. We're going to call them fragments for now, but they're basically the future pyruvates, the 3 carbons, but they're going to have these phosphates attached to them. And there's 2 major events that happen here. So first of all, we have to oxidize each one of these 3 carbon molecules, which basically means we're going to remove a hydrogen from it. And then we're going to take that hydrogen and we're going to add it to this ion right here, NAD. Now, NAD is going to be a big player when we get over into the Krebs cycle and the electron transport chain. So these are going to start cropping up in our conversation. And what I'm going to do is call these high energy molecules, NAD, the high energy molecule. So not high energy like this, but once we make it into that, it becomes a high energy molecule. And there's energy stored in that hydrogen that we just added to this ion of NAD. So we're going to rip this hydrogen ion off of our 3 carbon molecule, and we're going to put it on an NAD because we have to put it somewhere. We can't just throw them out. So they're going to go here, and that's going to store some energy that we're going to utilize much later on in this whole process. All right. So then what's going to happen is that our a second phosphate is going to be attached to our 3 carbon fragment. Not yet pyruvate, but going to be pyruvate molecule. All right, so up here was the energy investment phase where we utilized 1 ATP to get that phosphate and put it here, and then our second ATP phosphate, put it there. And now what we've got is we've got our 2 3 carbon molecules that have been separated. So I'm just going to follow one of these pathways, and we're going to take off a hydrogen and we're going to add it to our NAD to make NADH, and we're going to remove we're going to remove 2 of those. And then we're going to take a free floating phosphate. Yes, there are free floating phosphates intracellularly and extracellularly. And we're going to grab one of those and we're going to put a second one onto this 3 carbon molecule. Now, why are we doing that? Well, because we ripped something off here. You can't remove something without putting something back. That's kind of the way the story goes. So we removed a hydrogen over here. Actually, we removed a couple of hydrogens, and we're going to put a phosphate there in its stead. Now we end up with 2 3 carbon molecules that have 2 phosphates on them. So basically, we're going to have to do something with 4 phosphates in just a second. Can you think what we're going to do with these 4 phosphates? Can you think about these 4 phosphates? What are they going to become? Well, we're going to make 4 ATP, so keep your eye on those phosphates. All right, so phase 1, we've used a couple of ATP and took some phosphates and slapped it onto our 6 carbon glucose. And then in phase 2, we divided our 6 carbon glucose into 2 3 carbon fragments, and then we added another phosphate while in the process of taking off a couple of hydrogens, and then we added those hydrogens to an NAD and made a high energy NADH molecule out of it. All right, so now we're going to start off with our 3 carbon molecule fragment with those 2 phosphates on it. And what we're going to do here is we're going to start removing those phosphates, and we're going to reattach them to an ADP. And that's how we're going to create our 4 ATP. We're going to remove 2 phosphates from one of the 3 carbon fragments, and then another 2 phosphates from the other 3 carbon fragment. So this is the energy releasing phase. So in this phase, we're going to start off with our 3-carbon fragment with the 2 phosphates on it. And one of those phosphates is going to come off, and we're going to attach it to an ADP and make an ATP. There's one of our ATPs. We're going to remove this second phosphate. We're going to add it to a second ATP. So now we've made 2 ATPs by removing these 2 phosphates. And then we're going to do the same thing with this 3-carbon fragment over here, and we'll have made another 2 over here. And in the process, the enzymatic process that this 3-carbon fragment undergoes is basically going to be converted into a pyruvate molecule, also known as a pyruvic acid molecule. So we end up with 2 pyruvates and 4 ATP at the end of glycolysis. So to review glycolysis, although we produce 4 ATP, we have to utilize 2 to get the ball rolling. So we end up with a net of 2 ATP that are produced. So that's where this net 2 comes from. Now, what do we get in addition to these 2 ATP? Well, we produce 2 pyruvic acid molecules. Those are our 3-carbon molecules. And we also produce 2 of these NADH molecules, these high energy molecules, which are going to be utilized later on. So we kind of have to tuck those away for now. But this is what gets produced in glycolysis. Now, for glycolysis to continue, we have to have more of these NADs around in order to absorb the metabolites that are produced in this process, in order for us to have a place to put these hydrogens. But the thing is that we don't have an endless supply of NAD. So what happens then? Well, NAD is limited, and so we can only drive glycolysis as long as we have NAD available to accept that hydrogen proton. So that's the deal with that. So if oxygen is present, NADH will ultimately, this is later on, NADH will transfer that hydrogen to proteins in the electron transport chain, and all that's going to occur in the mitochondria, and that helps create ATP. If there's no oxygen present, then NADH will give the hydrogen atoms back to pyruvic acid, and it's going to convert it into lactic acid, and then the liver has to do something with it. So NAD ends up being a limiting factor in our glycolysis production. And there are actually some therapies in order to improve the metabolism of ATP that involve giving the patient NADH, or giving the patient NAD ions in order to absorb that extra hydrogen that gets produced when we're in the early stages of glycolysis. So yeah, NAD can end up being a limiting factor if you don't have enough of it floating around. Now, the active glycolysis doesn't require any oxygen, and we saw that as we went through each one of those steps. We have to have enzymes and phosphates available and NAD available to absorb the metabolites, but we didn't ever use oxygen in the process. So what happens to pyruvate? Well, pyruvate can do some energy creation without oxygen, and we call this anaerobic respiration. And the process that pyruvate, our 3-carbon molecule that we just created, the process that it enters is called fermentation. And what's going to happen here is we're going to take that high energy NAD where we added a hydrogen to it, and we're going to remove that hydrogen. And then that hydrogen is going to be added back to our pyruvate, our pyruvic acid molecule, and it's going to create lactic acid in the process. Now, what happens to lactic acid? Well, lactic acid is going to go back to the liver, and the liver, in its magical liver self, can convert pyruvate, convert lactic acid either into pyruvate so that it can join in the fermentation cycle again, or it can actually take it all the way back to glucose, and then we can go through that process again, glycolysis, and make ATP that way. So Mother Nature gives us some options if we don't have oxygen available. Now, most cells can function with anaerobic respiration to some degree. It's not an efficient process, but it can last for short periods of time. Glycolysis is faster at ATP production than aerobic respiration, but it yields far less ATP. So why is that an important statement to make here? Because keep in mind that our pyruvate, we've gone through the process to create pyruvate, which was glycolysis. We produced 2 ATP. We can then take that pyruvate, make it into lactic acid, shuttle it over to the liver, and either convert those molecules back to pyruvate or back to glucose, and then run glycolysis again and make some more ATP that way. So this process can end up being faster. Glycolysis can end up being faster than aerobic respiration, but we get far less ATP in the process. Because remember, every time glucose goes through ATP, it only gives us a net of 2 ATP in the process. And as we're about to find out, aerobic respiration is going to give us far more than that. When we have aerobic respiration, these are the chemical processes involving pyruvic acid and oxygen. And this gets us into the world of the Krebs cycle. Yes. And there's a couple of steps here. There's the Krebs cycle, also known as the citric acid cycle, and I'll tell you why it's called that when we get to that slide. And then there's this other process known as the electron transport chain. All right. So the big payoff with the Krebs cycle isn't so much the production of ATP, but it's the production of these NADH molecules, those high energy molecules, and then another type of a high energy molecule known as an FADH2. So Krebs cycle is going to give us a couple of ATP molecules, but we're going to create about 6 of these high energy molecules every time we go through the Krebs cycle. And then we shuttle those over to the electron transport chain, where we have the huge payoff in ATP production. Because NADH and FADH2 are going to be the molecules that create ATP over in the electron transport chain. But we still have to talk about the Krebs cycle, so let's do that. Now, we're at the end of glycolysis, and we've got our 2 3-carbon molecules here that we're now going to call pyruvate. And these don't directly enter into the Krebs cycle. We have to actually do a little bit of work to these 2 molecules in order to get them ready to go. And so there is this pre-Krebs cycle chemical reaction that has to happen. And you'll notice right here we have pyruvate, and there's our 1, 2, 3 carbons right there. And the thing that we're going to do is we're going to remove one of these carbons, and we're going to remove it as carbon dioxide. So there's a carbon-2 oxygen. It goes out as carbon dioxide, and we're left with a 2-carbon molecule right here. And we're going to add this this coenzyme A to this in order to create this molecule known as acetyl CoA, and it's this molecule, the 2-carbon molecule, that's going to enter into the Krebs cycle. So let's just review for a second. In the process of creating these 2 3-carbon molecules, we created 2 ATP. But now we can take these, and with a little bit of augmentation, we can get these guys ready to go through the Krebs cycle. And because we've created 2 of these molecules with glycolysis, we have 2 of these molecules that can enter into the Krebs cycle, which means we can have 2 spins around the Krebs cycle with 1 glucose molecule. Now, I've taken out a lot of the molecular structure just to simplify this cycle for you. So what I would like to point out is that we're starting out with our 2-carbon molecule right there. That's the one that came from pyruvate. So this is, let's just call it molecule number 1, one of our 3-carbon molecules, molecule number 1. And the first thing that you're going to notice is that we're going to join it up with this 4-carbon molecule right here known as oxaloacetate. And the thing that we're going to create first is citrate. Now, when we're talking about citrate, we can also say citric acid, because the ATE ending tells us that we're basically creating some sort of an acid. So the first step of the cycle is to create citrate, which is why we call it, or citric acid, which is why we call it the citric acid cycle. Now this is a 6-carbon molecule. It's not glucose, but it is a 6-carbon molecule. And you'll notice that one of the first things that we're doing is we're going to eliminate one of the carbons from our 6-carbon molecule and reduce it into a 5-carbon molecule. The other thing that you'll notice that's happening is that we create an NADH right there. Then we're going to take this 5-carbon molecule and we're going to do the same thing. We're going to eliminate a carbon in the way of carbon dioxide, and we're going to create another NADH. So kind of whenever we get rid of a carbon, we're going to create an NADH. And now we're into this 4-carbon molecule right there. Now we are going to remove something from this 4-carbon molecule, and in the process of doing that, we're going to create an intermediate that's going to create a molecule of ATP. So there's our ATP that we created. Now we still have this 4-carbon molecule on the other side of creating this ATP, but we're going to remove a hydrogen or two, and we're going to create this high energy molecule right here and end up with this 4-carbon molecule. And then we don't really have anything else that we can hack off of this. So we're going to add a water molecule to it to create a different version of our 4-carbon molecule so that we can remove a hydrogen and create this NADH, and then be left with oxaloacetate, which can then merge with another 2-carbon acetyl CoA. So that's the kind of the short version of what's happening here. So it's like Mother Nature is taking a 2-carbon molecule formerly known as pyruvate and a 4-carbon molecule that's been known as a number of things in this process, slaps them together and starts to use enzymes to remove different things in order to create different intermediates so that the stage is set to create high energy, let's go ahead and use a different color, high energy molecules such as NADH and FADH2, also to create an ATP, but mostly it seems to get these intermediates that allow us to do other things in the process, like join with a 2-carbon molecule, or create a scenario where we can donate that hydrogen and then donate another hydrogen. So that's really what the Krebs cycle is all about. It's just more or less using these molecules, adding things to it in order to be able to take things away and then create the intermediates that we need that are going to drive this process. So how are you going to learn this? I would learn it basically starting off with the concept of 2-carbon molecules and 4-carbon molecules, and then what can get removed to create what, which is, removing carbon dioxide and hydrogen, creating carbon dioxide and the NADH, doing that a couple of times, going through it that way. That's how I would learn this. Would I learn these names? I'm not for sure that I would really lean into a lot of the names. I think it's important that you understand that you make citrate and that you make alpha ketoglutarate, which is the 5-carbon, and then maybe succinyl CoA. But I'm not for sure that from this point on it becomes super important, because the major big event then is that we have to add water back in. We do have to add a water molecule back in to create malate in order to get this last NADH. So what I would learn, what I would take away from this, the thing that I would take away from this is that we make 1, 2, 3 NADHs and 1 FADH2 every time we spin the cycle. The other thing that we create every time we spin the cycle is that we make an ATP molecule, right there, ATP molecule. And then the other product every time we spin the cycle is that we make 1, 2 carbon dioxides. That's the other thing that I would make sure that I have solid when it comes to the Krebs cycle. I'm going to take a minute to erase all of this before I move on. Okay. So to synopsize what we just looked at in the image, the Krebs cycle, we've got 2 pyruvates that are going to enter the cycle. They enter as that acetyl CoA, which means that one glucose molecule is going to create 2 spins of the cycle. Each pyruvate gets a spin. Now, each step is either going to make a sacrifice, mostly a carbon or a hydrogen, and in some cases both. And there's only one step where we actually put something back in, and that's when we go from fumarate to malate. We have to add that water molecule back in. As a result of our one spin, we create 1 molecule of ATP. We create 3 NADH molecules and 1 FADH2. As a byproduct, we create 2 carbon dioxide molecules. And the thing that we have to remember is that our NADH and our FADH2 molecules are going to be tucked away for later because they're going to have to go over to the electron transport chain and do some more work. So what are we looking at here? Well, this is the electron transport chain. And so I'm going to point out that we've got this NADH here and our FADH2 here, and we got these hydrogens being shuttled around somewhere. So what's going on here? Well, let me get you oriented. This is all taking place inside of the mitochondria. And you might remember that our buddy, the mitochondria, is a two-membraned structure. We have an outer membrane, and then there's also an inner membrane. And then inside the inner membrane, we have something known as the matrix. So what's happening in the matrix? Actually, the Krebs cycle. Krebs cycle is taking place inside the matrix of the mitochondria. And the inner membrane of the mitochondria is the site of the electron transport chain. So as our image says right here, we're in the inner mitochondrial membrane. It is a bilipid membrane, just like most membranes are. And there is the matrix, which is right here, even says it, mitochondrial matrix right through here. And then here we're in the intermembrane space. So somewhere out here would be the outer membrane of the mitochondria. And you'll notice that we have a lot of these hydrogens populating this area, and then we're going to have a lot of these NADH, FADH characters playing around here in the matrix, because this is where they're made. Okay, it's where they're made. So what's happening here? Well, the first thing that we want to notice is that we've got these channels that we are shuttling these hydrogens through. And so it ends up being the job of the NADH to bring a hydrogen over here and drop off some electrons from the contribution of the hydrogen ions, and then shuttle these hydrogens out into the inner membrane space. And this is going to be an important feature here in just a second. Now, the high energy electrons that got donated when NADH dropped off its hydrogen are going to be shuttled from these different channels, or they're actually protein channels, so these are proteins, are going to go from protein to protein to protein, and then that energy is going to be utilized to fuel different chemical reactions. But the big payoff here, the big thing that is happening when we have that energy being shuttled around, energy being contributed to the electrons that we're shuttling around, is that we're going to be pumping hydrogens into the inner membrane space. Now, by the time we get done with these electrons, they're going to have lost a little bit of energy. But we're going to attach them back to a couple of hydrogen ions, making a hydrogen atom, a couple of hydrogen atoms. And we're going to take an oxygen molecule, and we're going to make some water in the process. So Mother Nature's a great recycler. We're basically taking a hydrogen and its electrons, separating the electrons, pumping the hydrogen atom and its neutron out into this inner membrane space, using all the energy in the electrons, because that's really where all the energy is, and pumping more hydrogen ions into this inner membrane space. And then at the end of it, we have to do something with those electrons, because the universe doesn't like electrons just hanging out by themselves. So we're going to attach them to a couple of these hydrogens that are still floating around in the matrix, hydrogen ions in the matrix, and find an available oxygen molecule and then make some water. Okay, so that's one thing that we're making here. Now, we're populating the inner membrane space with all these hydrogen ions. What's the big deal with that? Well, in addition to having these membrane-bound proteins, some of which are channels, some of which are enzymes, as part of the electron transport chain, this is the electron transport chain, the electrons being shuttled around from channel to channel. That's the transport part, and it happens in succession, which is the chain part. So in addition to having this electron transport chain with its different enzymes and channels here, all populating the inner membrane of the inner mitochondrial membrane, we're also going to have this structure, and this is another enzyme. This is ATP synthase. So what's happening here is that we're going to move the hydrogens out into the inner membrane space, and then ATP synthase is going to shuttle them back in. So ATP synthase is going to take these hydrogen ions and shuttle them back in. And when it does, there is this it actually functions like a turnstile. I know that sounds crazy, but there's this component to this enzyme, because that's what it is. It's an enzyme that when the when the hydrogen ion shuttle by it, it basically will spin this component in there. This is a structural component of this enzyme, and it basically acts like a firing mechanism or triggering mechanism that will then cause ATP synthase to catalyze an ADP and a phosphate into an ATP. And every 3 of these hydrogen ions that moves through ATP synthase will trigger the creation of an ATP. So that's why these NADHs are so important, is because they are carrying this hydrogen ion that is essential to populating this intermembrane space so that it can be brought back in to make ATP. And because we make so many of these NADHs and these FADH2s, we're going to have a lot of hydrogen ions available to make these ATPs. So this is really where the payoff is in ATP production. It's the electron transport chain and ATP synthase. So let's put all that together. So the electron transport chain and the movement of the hydrogens, that's taking place in the mitochondria across the inner membrane. The electrons are moved between 4 proteins, 3 of which are channels. Another one is basically like an enzyme, is a protein, membrane-bound enzyme. And what happens is that these electrons, they start out as very high energy particles, but that energy gets used to move the hydrogens into the intermembrane space. So by the time they get to that 4th enzyme, that 4th protein, they end up being relatively low energy particles. So the electron transport chain is going to be shuttling the hydrogen ions into the intermembrane space using the energy of these electrons. And the whole purpose of doing that is so that the hydrogen ions can be available to the ATP synthase later on to make that ATP. And then ultimately we're going to take those low energy electrons, attach them to a couple of hydrogen ions and make a water molecule. That's not on here, so I just drop that in. But then ATP synthase is going to be using all of those hydrogen ions in the intermembrane space, going to be using the movement of those hydrogen ions in order to create the energy needed to convert ADP into ATP. And this process right here, using ATP synthase, can produce roughly 34 ATP by utilizing the NADH and the FADH2 molecules that were created over at the Krebs cycle and in glycolysis. All right, let's talk a little bit about some other things that we can do regarding glucose. One of them is gluconeogenesis. So gluco means glucose, neo means new, and genesis means to create. So this is making glucose from something that is not glucose already, or fructose, or maltose, or any of the other sugars. It's basically taking a non-sugar type molecule and turning it into glucose. So what molecules do we utilize to make glucose? Well, pyruvate. Pyruvate comes from glucose. So we have enzymes that are capable of taking pyruvate and converting it back into glucose. Lactate, the liver does that. That's lactic acid, by the way. Lactate, lactic acid, pyruvate, pyruvic acid. So it's just different naming protocols, but they're the same molecules. Amino acids can be utilized to make glucose. Yes, my friends, we can take our bacon and turn it into sugar. Glutamine, glycerol, these are all molecules that can be utilized to make glucose. Now, why do we have this capacity? Well, the reason why is that some of the cells in the body can do this. They can take these different molecules and make glucose out of them, but some of our molecules cannot. So that if we have a shortage of glucose, most of the body cells can take other molecules and make glucose, which means that we're preserving the glucose population for the cells that cannot. And the cells that cannot do the conversion are going to be basically the brain and our red blood cells. Both the brain and the red blood cells, neurons in the brain and the spinal cord, cannot utilize any of these other molecules to make glucose, they expect to be fed glucose on a silver platter. So that if we are in some sort of a glucose deficit and our body is being called upon to use other molecules to create glucose, the body will preferentially reserve free available glucose for the brain so that the brain continues to function. Okay, so that's a little bit about what's going on with that. Pyruvate is a common starting material because we have it floating around, particularly these days when we can easily have carbohydrates available in our diets. And even though we know that we can go from glucose to pyruvate, and now we've just learned we can go from pyruvate back to glucose, it's not the same chemical reaction in reverse. It actually takes different enzymes to make pyruvate go into glucose. But we know that we have the enzymes available to do that. It's just different chemical reactions that go from, that get us from point B back to A. So, and why am I making a distinction about that? Because we've learned in a little bit of the chemistry that we've studied that some of our chemical reactions are reversible, which basically means that we can run that reaction from forward to backwards and don't really have to worry about what's going on with the chemical process. It's just basically some concentration gradients that are basically driving those processes. But with this process, going from pyruvate to glucose is a completely different set of chemical reactions than going from glucose to pyruvate. So they're completely different chemical reactions. It is not a reversible reaction. And anatomists always like to make a big deal about that. So now I'm making a big deal of it to you. All right, lipolysis, this is the breakdown of our stored fats. And when we break down our fats, we've got these fatty acids. We're going to break it down into glycerol and little fatty acid chains. And it is actually the reverse of lipogenesis, which is the creation of fats. So fatty acids are a fuel source that are preferred by some cells in the body, such as liver cells, cardiac cells, and skeletal muscle. They actually prefer that. They prefer fatty acids as opposed to glucose, which is interesting. So we do need fatty acids in our diet. Fats are not necessarily altogether bad. Some fats are better than others, so it is good to be mindful of that. And it's good to be mindful to move when you're going to be eating them. Lipolysis is accelerated when carbohydrate intake is inadequate. So what does that mean? That means that if you reduce your carbs, then your body will preferentially utilize fat for fuel. We all know that. That's what we're taught from the beginning of of our moment when we realize that food is fuel and fat is fuel that has been stored. So that's kind of one of the bases that we learned. So yeah, if you reduce your carbohydrates, then your body's going to look first of all to your fat stores, and start converting your fat into glucose or glucose precursors. I'll put it that way, because we're going to get into what actually gets created. So when we metabolize fatty acids, what we actually produce is acetyl CoA. Acetyl CoA. Acetyl CoA. Where did we see acetyl CoA? This was when we took pyruvate and turned it into the 2-carbon molecule known as acetyl CoA before dropping it into the Krebs cycle. So yes, we can take fatty acids and convert it into this acetyl CoA. Just like we could take glucose, convert it into pyruvate, turn pyruvate into acetyl CoA. So whether we're doing glycolysis or whether we're metabolizing fatty acids, we basically end up with the precursors that are going to go into the Krebs cycle, which is going to lead us down the pathway of Krebs cycle, electron transport chain, and ATP synthase. All right, so the acetyl CoA is the molecule that's going to enter into the Krebs cycle. But it is dependent upon whether or not we have that 4-carbon molecule available to bind with it. Because remember that 4-carbon molecule that came around at the end of the cycle? We called it oxaloacetate. or here I've got it listed as oxaloacetic acid, same thing. If we have enough of that available, then this acetyl CoA can create a bunch of ATP for us. So this is the beauty of burning our fats. We create a lot of acetyl CoA that gets to drop into a Krebs cycle in the mitochondria and start producing ATP. But only if we have enough of this oxaloacetate available to combine with it. Now, what happens if we don't have enough of that 4-carbon intermediate in the Krebs cycle to join up with our acetyl CoA? Well, if that's not available, then the acetyl CoA will accumulate. And when that happens, when we have an accumulation of acetyl CoA, it gets converted by the liver into ketones. So the liver is going to do something with that 2-carbon intermediate, and it converts it into ketone bodies. Now, if there is excess acetyl CoA, it's basically going to overload the Krebs cycle and become ketone bodies. And you might be asking yourself, well, why is it that we would make so much acetyl CoA? Well, it comes into understanding what makes up a fatty acid. A fatty acid chain is basically a series of carbon molecules, and it can be upwards of about 17 carbon molecules with their hydrogens coming off of them, little hydrogen molecules like this. And what ends up happening, in order to make these 2-carbon molecules, we're going to cleave this big long chain of fatty acid chain into these 2-carbon molecules. So let's say that we had a 16 carbon chain fatty acid. That would give us basically 8 acetyl CoAs. So we don't get 8 acetyl CoAs from a glucose molecule, we only get 2. So you can see how very quickly a fatty acid chain being metabolized into a 2-carbon molecule can end up overloading the Krebs cycle. So that's why we say if we burn fat too efficiently, if we break it down too efficiently, we can overload the Krebs cycle. And we have to do something with all this acetyl CoA floating around. All right. So if there is excess acetyl CoA, it overloads the Krebs cycle. And in this process of converting it into something else, we have to, in the process of converting fatty acids into something else, we have to be mindful of having an escape route, I guess is how to say that, having some other mechanism to mop up all this extra byproduct that we made due to fat metabolism. So what happens here is acetyl CoA gets converted into HMG CoA, and then HMG CoA gets converted into beta hydroxybutyrate, which is basically a ketone body. So this is just giving you some of the details that if we overload the Krebs cycle with acetyl CoA because we metabolized a bunch of fat, we're going to make ketone bodies out of it. That's what this slide is telling you. Now, metabolizing ketones is an alternative pathway for glucose-dependent tissue to get energy. So ketones can be produced faster than they're used, so it ends up being an abundant supply of energy. But the breakdown of ketones creates carbon dioxide and acetone. Now, that's not altogether bad because we can exhale both of those, but it's not normal. It's not a normal pathway. And the person that is utilizing their fat at a rapid rate typically is going to have a smell of sweetness on their breath, and that's going to be due to the acetone being exhaled. So let's think about this for a moment. Let's say that you had a person who is diabetic. The person who is diabetic doesn't have, let's just say that there's no receptors available for insulin. So glucose cannot get into the cell, which means glucose cannot be processed through glycolysis, and then we can't get that intermediate pyruvate to make acetyl CoA to enter into the Krebs cycle to make all that ATP. So The diabetic cannot utilize glucose to make energy. So what are they going to use? They're going to use fats. They're going to start metabolizing their fats. So if you have a diabetic who isn't making insulin, or whose insulin is not being picked up by the receptors, then their body will preferentially begin to utilize their fat. And that only lasts as long as the fat stores are available. And the way that you know that a person may be dealing with an insulin imbalance or some challenge to their glucose metabolism is that their breath will smell sweet. That is your clue that they're utilizing fat instead of glucose for energy. They're making tons of ketones and they're burning them. Okay, so we know that ketone bodies are when we basically have made the, we've used fat we've broken down fat, made the ketone bodies, and now we can use ketone bodies as our fuel source. But what about making fat? Lipogenesis. Well, we know the body's really good at that. Plenty of us have evidence of that. So yeah, we can actually make fat. It occurs when cellular ATP and glucose levels are high. So if we have a lot of glucose floating around, the body can, and the energy to do so, we can actually make fat. Now, dietary glycerol and fatty acids are not needed to do this. Oh, isn't that good news? We don't need the parts of triglycerides to make it. We can just make those parts ourselves. So yeah, body's really efficient in making fat, and there's a reason for that. We didn't always, as a species, walking planet Earth, didn't always have an abundant food supply as we do now. So it behooved our bodies to come up with a mechanism that could store food for later. And that's what fat's all about. So our chemistry is designed to make sure that we can easily store extra food for fuel later on. That's a whole point of that. When we take our excess that we take in, we're going to store about half of it into adipose, and then the other fat can be deposited in other areas around the body. So when we start storing fat, it goes around our organs, it goes underneath our skin, then it goes into other areas like, maybe fat pads around the eyes or the bottom of the feet, things like that. Now, glucose is easily converted to fat because it has that intermediate acetyl CoA. So let's think about this. Let's think about that statement right here. This is very important. Okay, so we learned that we can take a glucose molecule, which is a 6-carbon ring, and through glycolysis, we're going to make 3 carbon molecules, 3 carbon molecules. I'm going to write it that way. Carbon with 3 molecules. We're going to have 2 of those, and then those get to be created into acetyl CoA. And I'm just going to write ACO, which is our 2-carbon molecule. All right. So acetyl CoA ends up being this magic fork in the road in the chemistry of either taking glucose and turning it into fuel, or we stop right here and say, hey, we've got a lot of this 2-carbon molecule. Can we store it? And the body can say, yeah, as a matter of fact, we can. We can take these little 2-carbon chains and start linking them together, and we create a fatty acid. So let me say that again. We can take our 6-carbon sugar, right here, 6-carbon sugar, and we know that we can run it through glycolysis, make a couple of ATP out of it, make this 3-carbon pyruvate, and then start to convert it, this is pre-Krebs cycle chemistry, into our 2-carbon molecule. And the body might say, you know what? We've already overrun all of that 4-carbon intermediate in the Krebs cycle, and we're just going to make a bunch of ketone bodies with this, but I'm not sure we really need them. Can we store this 2-carbon molecule as fat? And so the body will take these 2-carbon molecules and start to string them together in the form of fatty acids, and then we get to store it. So acetyl CoA becomes that magical fork in the road, that chemical fork in the road, where we can either use that as fuel whether we drop it in the Krebs cycle or whether we convert it into ketone bodies or whether we make it for fuel in the future and turn it into fatty acids. Now we have another cycle called the urea cycle. And this is when we take ammonia ions and degrade them. And the body doesn't handle ammonia ions very well. So we have to have a way to convert that quickly into something that is a little bit more easily tolerated in the body. And you might be saying, well, where are we getting our ammonia molecules from? Where our ammonia molecules actually come from the breakdown of proteins. So you might remember that proteins are made up of a nitrogen hydrogen combination at one end, nitrogen and hydrogen, and then we have a central carbon, and then we have a carboxylic acid group here at the other end. When we break down our nitrogen right down here at this end, we end up creating ammonia. Because ammonia, the ammonia molecule, if we come down here, is NH3, but it can also pick up another hydrogen and become an ion of ammonia known as NH4. And this is the molecule that we need to turn into urea, because when we start breaking down our proteins, we create ammonia. So that's the urea cycle. So ammonia is produced in amino acid breakdown. We call that transamination. Basically, we're removing the amine group, the nitrogen, and the hydrogens. And urea ultimately is eliminated by the kidneys. So we get ammonia from breaking down proteins. It gets converted into urea, and obviously not even introducing you to that chemical, so it's not, at least the chemical structure of it, so it's not that important to you. And then but you do need to know that urea can be, that urea is tolerated. It's a waste product. It's tolerated in the tissues more easily than ammonia, but then we eliminate it largely in the kidneys. So there's language around when we eat and when we're in periods of fasting, and that's what this section is. So let's talk about the absorptive state. This is known as the fed state, and this is when our anabolic processes are outpacing our catabolic processes. So anabolic processes are when we're building, not necessarily tearing down. So this is what's happening, we can think of in the tissues. So we have the breakdown of the macronutrients, the sugars, amino acids have entered the blood and are now available for our tissues to do something with them. So that's why the anabolic process is outpacing it, because we've already done the catabolic process, already taken the macronutrients and broken them down into the micronutrients for our tissues to do something with. This is when we see the release of insulin. And the reason why we release insulin is to allow glucose to be swept into the cells. Physical activity following the fed state is what causes consumed sugar and fats to be used as fuel. So there has long been this idea that after you eat a meal, you need to sit down and do nothing. But we've now have a better understanding of what's happening in the body, so that after you eat a meal, it's not actually a bad idea to take a walk, because you've eaten the meal, your body's doing some digestion, and then an hour or so later, get up and take a walk, and you will preferentially utilize that food that you just ate as fuel, less likely to store it as fat. And if we think about it, that's kind of how the process should go. You eat your food, you maybe sit down for an hour, allow the metabolic processes to break the food down, and then it makes its way into the bloodstream, and now your tissues are ready to do something with it. And if you give your tissues something to do, i.e. activity, then that fuel that you just ate will be utilized as fuel and not stored as fuel. All right, now I want to talk a little bit about this comment right here. Glucose moved into the cells, gets converted into glucose 6-phosphate. What does that mean? And then it goes on to say it maintains a concentration gradient. Well, when we move glucose into the cell, we're going to have to, we largely rely upon the concentration gradient in order for that to happen, because all insulin does is open the door and glucose goes inside the cell. Now there's going to come a point where the glucose outside the cell is going to be equal to the glucose inside the cell. But we still want to move all the glucose, or not all of it, but a large amount of it inside the cell. So how do we do that? Well, Mother Nature, she's very clever. She makes all the rules here. And she says, well, if I have glucose molecules on this side of the membrane and glucose molecules on that side of the membrane, a concentration gradient gets created, which means that glucose will move from an area of high concentration to an area of low concentration. Let me see if I can draw another picture. I'll use purple. So we've got a lot of glucose over here, let's say outside the cell. And maybe we don't have very much glucose inside the cell. So as we start to move glucose inside the cell, eventually we're going to create just the opposite, where we're going to have a lot of glucose inside the cell and not very much outside the cell. And with an open door, where's that glucose going to want to go? Well, it might want to go back outside the cell, or it might just create a concentration equivalent, where we have the same number of glucose molecules outside the cell as we have inside the cell. So how do we basically encourage glucose to keep moving inside the cell? Well, we have to hide it. And the way that we hide it is we add a phosphate to it. Because when Mother Nature's creating a concentration gradient, she's not creating concentration gradients between a whole bunch of different molecules. She's creating concentration gradients against one type of, with one type of a molecule. So when a cell brings in a glucose, it slaps a phosphate onto it, and that basically changes the molecule, and the concentration gradient remains just with plain old glucose molecules, not glucose molecules that have been phosphorylated. So the cell cleverly hides glucose from the concentration gradient, thereby maintaining what appears to be a lesser number of plain old glucose molecules inside the cell from outside the cell, and that causes more glucose to be ushered inside the cell. So Mother Nature being a very clever girl, encouraging cells to hide their glucose molecules as soon as they get moved in by adding phosphate to them. And there's always plenty of phosphate inside the cell, because what does the cell do? It's making and using ATP. It's always removing a phosphate or adding a phosphate onto something. Sometimes it's an ADP if we want to make another ATP molecule, and sometimes it's a glucose if we want to hide it. So if the absorptive state is the fed state, the state in which our cells are able to take up the micronutrients, then the post-absorptive state is what we are in when we have utilized all of those. And we might call this the fasting state. So the food's already been digested, it's been metabolized, it's been absorbed into the bloodstream, and our cells have done something with it. Okay, so at this point, any more glucose is going to have to come from glycogen, our stored glucose levels. And the body's always seeking to maintain a blood glucose level of about 80 to 120 milligrams per deciliter of blood. All right, so it's going to be the pancreas looking at these numbers, and if we see the numbers starting to edge too low to that 80, then the pancreas will release glucagon that's going to trigger glycogen to be released from the liver, or maybe even from our skeletal muscle, because we always store a little bit there too. Now, what happens if you have a prolonged fast, where you've ripped through all your glycogen stores, and maybe you're even tapping into your fat and you're burning ketone bodies, and you got that sort of thing going on? Well, the liver, clever liver that it is first of all going to work to restore glycogen levels. And so one of the first things that it's going to do is it's going to convert glucose into glycogen, and it's going to start to convert the glucose into fatty acids to restore your fat stores. So this is why fasting as a diet doesn't work, because you're basically sending your liver into this this process where it's just waiting for you to eat something. So the liver interprets your fasting as a scenario where we might die if we don't get food. And so it's waiting for that glucose to hit it, that next big wave of glucose to hit it. And when it does, it's going to store fat to save you. So this is why fasting as a diet protocol, long-term fasting as a diet protocol, isn't a good idea. Now there's a whole different mechanism with intermittent fasting. It actually improves metabolic processes. And intermittent fasting basically means that you reduce calories for a very short period of time, like a day or even a few hours in the course of a day. But it actually improves overall body chemistry with regards to metabolism. But that's an entirely different process. It's not one that the body perceives as detrimental. It actually perceives it as a normal daily cycle that it can contend with, or longer term cycle. So intermittent fasting is different than prolonged fasting. So don't go into the woods, into the wilderness, and fast for 40 days, because you'll just you'll put on a lot of fat afterwards. Your liver's trying to save you from yourself. Now, starvation is when the body's been deprived of food for an extended period of time. And when that's the case, then the priority of the body is to supply the brain with glucose, because we can't function without the brain. So glycolysis will shut off in any cell that is capable of using another molecule for a fuel source. So in its wisdom, the body will say, let's say that it's a muscle out in your thigh. The muscle will say, hey, you guys notice that we haven't had anything to eat for a while? And as a result of that, that skeletal muscle in your thigh will say, I know the brain's going to need the glucose, so we're not going to do glycolysis anymore. We're actually going to start to utilize other sources for fat. We're going to start to look at, first of all, fat. We're going to break down fat, lipolysis. And then if things get really rough, we'll start breaking down proteins. So that's what the body goes through in the starvation mode, is that it recognizes that there hasn't been an intake of calories in a while, hasn't been an intake of nutrition. The cells will switch off glycolysis, start utilizing fat first. So fatty acids are going to be converted into acetyl CoA so that we can still maintain the Krebs cycle. All right, that's the first thing that happens. And maybe even pyruvate and lactic acid from the muscle will be shuttled over to the liver to get converted to glucose, and then that glucose will be shuttled to the brain. Glycerol from the fatty acids, because remember the glycerol is the backbone that our fatty acids are attached to, that will be utilized to make glucose as well. We got to feed the brain. So the cells of the body recognize now that we're kind of in a dire state, and we need to do a couple of things. We need to fuel our body cells, but we also need to fuel the brain. So it starts to switch over and make the products necessary to make glucose for the brain, and then acetyl CoA for the body cells to keep ATP going. Now, after several days of tapping into our fat stores, remember we're going to be creating an abundance of those 2 carbon molecules known as acetyl CoA. Because as we burn those fatty acids, we're going to be taking those long fatty acid chains and making 2 carbon molecules out of them. So we're going to overrun our system with acetyl CoA. And as a result of that, we're going to be making ketone bodies. Now, the heart and many of our organs are going to prefer to use ketone bodies for the fuel source. All right. So we're doing this, we're utilizing these fatty acids to make ketone bodies, basically to prevent the breakdown of proteins for glucose, because we want to preserve proteins. Proteins are structurally important to the body, and they are also chemically important to the body. But there's going to come a point when we deplete our ketones, when we deplete our fat, and when that happens, then the body will turn to protein as a last resource to make glucose. Now, our metabolism is defined as all the chemical reactions that our cells can do, all the chemical reactions, whether it is catabolic, breaking down substances, or anabolic, reassembling our micronutrients into larger molecules. So that's what our metabolism is defined at. Our metabolic rate is the total heat produced by those chemical reactions and by the mechanical work that gets done in the body. So that's what our metabolic rate is. And we can measure that in a couple of different ways. We can measure it directly through use of a calorimeter, which measures heat liberated into a water chamber. So yeah, we can measure it that way, or we can measure it indirectly through a I want to say respirometer. I think it's actually said respirometer, which measures oxygen consumption, which will tell us about heat production. So there's a couple of ways that we can measure that, and I think that using respiration is the easier way of determining metabolic rate. Now, the basal metabolic rate reflects the energy needs of the body in order to perform its most essential activities. So this just basically means the activities of keeping you alive. 70% of our energy is going to go to basic body functions. That is just doing cellular activities to maintain life. 20% of our energy is going to go to physical activity, and then 10% is going to go to controlling body temperature. That's actually quite a bit when you think about it. So our body works really hard to maintain body temperature. All right. So that's what our basal metabolic rate is. So how much energy are you using to maintain you? Doesn't take into consideration how much you're using when you're on a jet ski or when you're running the marathon. Basal metabolic rate is just how much does it take for you to sustain life. Basal metabolic rate is going to be influenced by a number of things. One is your age. When you're young and you're healthy, your cells are all energized and capable of doing amazing things, recuperating really quickly, your metabolic rate is going to be rather high. As we age, cellular activity tends to slow down, so basal metabolic rate is going to slow down as well. Gender is also going to play a role. Males have a disproportionately higher basal metabolic rate than women do, and there's some speculation that it is because of greater muscle mass, greater bone density. Just the male body has more to it. I'm gonna back up and say it has more biologically active cells than the female body, which has a fair amount of fat to it. And I know that fat cells are biologically active, but they're designed to do different things. So yeah, the males have a higher metabolic rate than females do, which is why dudes can eat more than women do and not gain the weight. That's really the bottom line. Body temperature, basal metabolic rate is going to increase with your body temperature. So for example, if you're in a fevered state, your metabolic rate is going to go up. I think we got kind of a chicken egg sort of thing going on there. So pyrogens, you might remember from our unit on the immune system, that pyrogens get released as a result of infectious states, and pyrogens are the chemical messengers that are going to tell the hypothalamus that we need to elevate our body temperature, and so the hypothalamus will send out the signal to the body cells that they need to ramp up their activity. Now, when body cells ramp up their activity, that means that they're ramping up chemical processes. Chemical processes release heat. So when the cells become biologically more active, then we end up with a higher body temperature, and as a result of that, we're going to have a higher basal metabolic rate. So I hope that kind of sheds light on why that is the case. When you have an active cell, you're going to have a higher basal metabolic rate. Stress can actually increase your metabolic rate. That's why a lot of people actually lose weight with a certain amount of stress, is because it can drive your cells into higher activity. Unfortunately, stress also drives elevated cortisol levels, which can cause some people, just depends on your body type and the type of stress that you're dealing with and what you do throughout the day, to actually gain weight, because it can be driving you to eat more in order to maintain blood glucose levels. Now, thyroxine is the hormone that's made by the thyroid gland. And I like to call thyroxine the go hormone because it makes your cells do their cellular activities. So thyroxine increases oxygen consumption, which means that it's going to drive cellular respiration, and it can increase basal metabolic rate. So people who have hypothyroidism are going to have a lower basal metabolic rate. People who have hyperthyroidism are going to have a higher basal metabolic rate. So that's why you can tell a low thyroid function patient, because they have a tendency to be kind of heavy. Their cells just aren't as biologically active. They have a tendency to put on weight. Whereas the hyperthyroid patient is the person who has a high basal metabolic rate, tends to be rather thin, maybe even a little bit on the anxious and jittery side. Now, what are the ways that we can manage heat? Because that's an important feature in the body. Well, we can radiate heat. So heat transfer by way of infrared waves is radiation. And believe it or not, 60% of our body heat is lost through radiation. So basically, the fact that you're sitting in an air environment, you are radiating out your body heat. So I'm showing you an image here of a campfire. So your logs are burning and they are radiating heat. And you put your hands there if you want to warm your hands up, because you know that there's heat radiating off of that burning log. So radiation is a way that we do that. Another way that we can move heat around is through something called conduction. So this is heat transfer as a result of two different conductors, I'm going to say that way, being in direct contact. For example, let's say we've got somebody who is holding a metal rod, and heat can be conducted from the hand into the metal rod. Heat can be conducted into the rod by way of a candle. But as that heat travels up the metal rod, then the heat can then enter the hand. So all of these are mechanisms of conduction. So we can, if you were just holding a metal rod, you would be conducting heat into the metal rod. If you had a metal rod, just putting the metal rod in the candle, that's going to conduct heat into the metal rod. But then the rod can conduct heat into you as well. 3% of body heat is lost through conduction. So by virtue of the fact that you are in contact with something else aside from air, you are moving your body heat into that other substance. It might be another person. It might be a metal chair that you're sitting in, on, or the bleachers at a stadium, but you can lose heat through conduction because you are depositing your heat into another substance. Now, convection is an interesting concept because it involves components of radiation and conduction. So convection is when basically you have a scenario where you have heated up the environment around you, and that environment has been energized by your heat and moves away from you, allowing lower energy components of that environment to now come in contact with you and get heated up. So what we're showing you in this image here is that we've got a vat of water over a heat source. And as the heat at the bottom of our vat or our tub of water heats up, it's going to move to the surface. The hot water moves to the surface because it gets energized and moves around, and the lower energy water, the cooler water, actually makes its way to the bottom and gets heated up, and we create this circular motion. That is the convection that we're talking about. So you can see how then hopefully that we had a component of radiation. Heat got radiated into the water. And then we had conduction, the heat entering into the water, and then we have convection, which is the movement of the water around so that the cooler parts then are able to absorb the heat. So if you were in a swimming pool, your body starts to lose heat. It radiates the heat out, it goes into the water. The water is going to absorb the heat, that is actually conduction. And then as the warm water gets energized, it moves away from you and allows the colder water to come in next to your skin, and then you get to radiate your heat into that water. It will absorb it by way of conduction, and then through convection, it will move away from you and allow cooler water to come in. 15% of body heat is lost through some sort of convection mechanism. So you might be thinking, well, I'm not in a vat of water, Dr. O. I'm not, can't be losing that much. Hello, sweat. That's what sweat does. And just if you need an explanation, if you sweat, then you put water on your skin, and your body heat will radiate into the water, and the water will evaporate. The water that's in contact with your skin, direct contact with your skin, those molecules will evaporate away, leaving the water that wasn't in contact with your skin, now in contact with your skin, to absorb your body heat through that you're radiating. It will absorb it through conduction and then evaporate. And basically, you're creating your own little micro convection. So I just talked about this, evaporation. This is when we transfer heat via water changing from the liquid state into the gaseous state. So if we look exactly what's happening on our skin, we radiate heat. The heat gets conducted into the water, aka our sweat. And the water molecules will get so jazzed up that it forces them to change from a liquid state into a gaseous state. And that is evaporation. So basically, when evaporation, when we move from a lower energy state like liquid into a higher energy state like gas, then that energy gets transferred with those water molecules. So that is the mechanism that evaporative cooling actually provides for us. Now, like I said, we can tease each one of those phases down, like your body radiating the heat, the water absorbing it through conduction, and then the water molecules evaporating, and then we have that convection where the cooler water molecules are now in contact with your skin. 20% of body heat actually gets lost through evaporation. So basically, as your water molecules lift off your body, they're carrying the heat with it because they are now in a higher energy state of gas, and they have to be, that higher energy state has to be fueled by something, and it gets fueled by your thermal energy. So let's take a look at some homeostatic imbalances. We're going to start off with hypothermia. So hypo means low, and thermia means condition of being warm, basically. Thermal means heat. So this is when your body core temperature drops to about 35 degrees Celsius or 95 degrees Fahrenheit. And what happens at this point is that the heart and the nervous system begin to fail. Both of these involve nerve conduction. Because remember, the heart has the intrinsic conduction system. It has its own nervous system. These begin to fail. So what does the hypothermic patient look like? Well, they're going to be shivering because they're going to have neurological compromise. They'll have slurred speech. Their breathing, because remember, breathing is largely controlled by the medulla, can start to become very shallow and slow. Blood pressure is also somewhat controlled by the medulla oblongata. Blood pressure can become very weak, and so they're going to have a weak pulse. They'll have lack of coordination, again, another neurological function. Drowsiness may be a component of this as body systems start to shut down. Confusion, that's a neurological component, and loss of consciousness, also another neurological component. So you look for any sort of neurological component, and these are the big ones that are most obvious. So how do you prevent hypothermia? Well, you dress warmly if you know you're going to be in a cold environment. How do you deal with a hypothermic patient? Well, you want to rewarm the body, but you want to make sure you do it in a slow fashion. And actually, the best source of heat for a hypothermic body is a couple of non-hypothermic bodies. Certainly, you can do it with warm water bottles, things like that. But if you're in a environment where you can't get rescue immediately, and somebody has gotten chilled too much because of being outside too long, trying to do whatever, trying to help everybody, then the best thing for you to do is a lot of blankets, and a couple people get under the blankets with them. That's the way you handle that in a survival situation. Now, on the other end of the spectrum, heat cramps. This is what happens when you get too hot. All right, so these are painful muscle spasms that occur when you've been super duper hot. And these are different than something like a Charlie horse. These don't go away in just a few hours. They last for hours. And the reason why they occur is because you've had a loss of fluid and a loss of electrolytes. And so you're getting this weird crampy spasm because you've just got the electrolytes not being where they're supposed to be in your muscles. And the thing is that it tends to involve the muscle groups that may have been being used at the time. So if you're outside and it's 95 degrees and you've got a yard that you want to mow and hedges you want to trim, and you're outside doing that, and you don't rehydrate and you don't keep your electrolytes in place, that evening, guess who's going to get cramps in their hands and their forearms? Yeah, that's not an uncommon thing to have happen. So yeah, you're going to end up getting the cramps in the muscle groups that you were using a lot when you got overheated and dehydrated. So how do you deal with this? Well, you want to restore your fluids, you want to restore the electrolytes, you want to rest, cool down, and when those cramps start in, just be really nice and try to stretch it out. Let's try and stretch it out. All right, then we have heat exhaustion. And this is when you get sick because you've been exposed to high temperatures for a while. And this patient is going to look rather odd because they can have heavy sweating, yet the skin is cool and pale. They can have muscle cramps, they can be dizzy, they might even faint. They'll have a headache, they'll be tired. So this person doesn't look right. Like I said, they're pale. Their skin is cool to the touch, but they're also sweating. So how do you deal with this person? Well, you want to move them to a cool location. You want to sit them down, have them rest, have them sip some water, and just try to bring the body temperature back down a little bit. Then there's heat stroke. And this is a serious condition, and this is when the body temperature rises to over 103 degrees Fahrenheit. So what does this patient look like? Well, their skin is hot, it's red, it may be dry, it may be damp. They're going to have a strong, fast pulse. They may have a headache, they may feel dizzy, may faint. They may be a little bit confused, they may feel nauseous. All right, so this is considered a medical emergency. When the body gets too hot, we can start to have impairment of enzymatic reactions. We can start to do cellular damage. So this is why this ends up being a medical emergency. With this person, this is a moment when you call 911. You immediately get them into a cool location, try to cool them down, maybe put some water on them. I don't think you want to give them a great deal of water in case something else more serious should transpire, such as they faint, they begin to vomit. That sort of thing. So this person, you would want to apply cool compresses, try to get them cooled down. So it's an odd thing to see somebody whose skin is bright red and they're not sweating. That's usually a pretty serious sign that something's going wrong and they need to get into air conditioning. Pyruvate dehydrogenase complex deficiency is a fairly rare mitochondrial disorder where the body cannot metabolize a certain molecule. So it's a rare, like I said, rare genetic disorder. It can have a wide range of symptomology, and it can also manifest at different set points in a person's life. Most cases involve poor feeding, which basically means that the body is not capable of breaking down the food that you ingest. That's what we mean by feeding. So the person, because they're not able to do the correct metabolic processes, can't get the micronutrients into the blood and feed the tissues. That's what we mean by poor feeding. This patient will have lethargy, so they're low energy. They might have rapid breathing due to lactic acid buildup, because remember, we're trying to utilize different metabolic pathways in order to get that glucose and make that ATP. Another sign of a person who is suffering from this is that they may have poor muscle tone, and they may begin manifesting neurological issues. There's no treatment for this disease, but lactic acidosis can be treated. So we would be treating the byproducts of the disease, the symptomology of the disease. Because it is a disorder of carbohydrate metabolism, the sort of diet that is recommended for this patient is ketogenic. So we want to basically have a diet that is low in carbs, high in protein and fats. Then we have phenylketonuria, which is a rare genetic disorder that causes amino acid phenylalanine to accumulate in the body. So we can't break this down. Now the symptoms with this patient is that they have a musty odor. This is due to chemistry. They might have seizures, skin issues. This patient typically has light skin and light colored hair. They may be that tow-headed child. They have a relatively small head size for their body size, and there's usually some sort of a delayed mental development with this patient. People who are born with this, the parents usually know it. And it ends up being a lifelong treatment in order to help this patient progress as normally as they can through life. So treatment's going to involve a diet low in phenylalanine. They'll have to take nutritional supplements to ensure that enough nutrients are consumed for growth. But this patient will always have a little something that's off. They tend to be a little bit slow developing. They're not necessarily mentally retarded and have to be held back in school, but they tend to be just a little bit slower. There is a neurological component with this as a result. Obesity is defined as the accumulation of excess body fat, and that a person who has a body mass index of over 30 is considered to be obese. The problem with obesity is that it leads to higher incidence of atherosclerosis, type 2 diabetes, hypertension, heart disease, and osteoarthritis. So there's a number of known health issues correlated to excessive body fat. More adults and children are overweight now than even 20 or 30 years ago, and it's largely due to the massive changes that we've seen in our culture. Largely due to technology and the way that we live our lives. 20 years ago, 5% of children were overweight, but today it's like at least 15%, if not greater. Now, obesity is actually a rather complex condition because there can be components of genetics that play a role in this. It could be behavior that plays a role. There could be metabolic processes in the person's own body that are challenging, as well as different hormone levels. And we certainly are more aware now than we were even just a few years ago of many things in our environment that can mimic hormones and create a little havoc. So there's a number of factors that go into creating obesity, and I think that we're challenged in a lot of ways in today's environment in order to get our weight down as a result of that. Now we know that that contributing factors are going to include things like inactivity, but it can also include medications. There's also disorders such as Cushing's syndrome or hypothyroidism, and we're learning that those can be triggered from a number of different other avenues that can also lead to obesity. Lack of sleep can contribute to obesity, stress, as well as disruptions in the gut microbiome. So just this short list right here tells you that there's a number of things that can create a scenario that favors obesity over healthy body weight. So treating obesity typically involves dealing with multiple aspects of a person's life. So it can involve lifestyle changes. So it would have to be stress management. You might have to go through counseling, learn techniques to deal with anxiety, eliminate sources of anxiety and stress from your life. And that can be huge. That may mean a whole lot of different things for people. It may mean learning a different way of eating. So that's your dietary changes. Maybe it means figuring out food sensitivities, food allergies. You may have to be dealing with some sort of hormonal environment. There may be hormonal imbalances. There may be components in your environment that are leading to allergies that are driving certain processes. So if you are an obese person, it's not, and it's so easy for society to go here. People tend to condemn the obese as a character flaw when there could actually be a lot of different things that are driving that process in an individual. So, yeah. As a healthcare provider, it behooves you to approach that patient with a great deal of compassion, because it might not be as simple as reducing calories. There may be a lot of things going on there. So a lot of people deal with vitamin and mineral deficiencies, generally because of a poor diet. You're just not taking these things in, and we do have to take these things in. And you might remember from earlier in the lecture, many of our vitamins and minerals are eliminated very quickly out of the body, except for our fat-soluble vitamins, which can be stored. So the body is pretty careful about not allowing these things to build up, which means that you have to be eating a pretty constant source of them. So if you're not eating a good diet, a good diet that includes a mixture of vegetables, then you could be functioning in some sort of a mineral or vitamin deficiency. And because we have so many minerals and vitamins that we need, the symptomology can be pretty varied. So for example, if you are lacking vitamin A, you're going to see this in vision changes, because we need vitamin A to support the retina, and it can also affect the skin. We need vitamin A in the skin. Vitamin B12 and iron can lead us down the path of anemia. Lack of vitamin D can create all kinds of things, not just bone abnormalities, certainly bone abnormalities in the developing human, but it can create neurological issues in the adult, depression being one of them. Vitamin K, blood clotting disorders. So these are just some examples of symptomology based upon vitamin deficiency. So how do we treat that? Through supplementation. And sometimes it's more than just going down to the store and buying, that bottle of Flintstones vitamin and taking them. You might actually need to do injections for a while to get your body back on track. And with that, we are done.